Okay. So I believe we're talking about stability, right? And so we're trying to figure out which resonance structure is more stable between the two, right? And so if we take a look at this, we would predict this one would be more stable. A would be more stable than B, right? Because you have the two separate charges. And then in the case of C and D here, so then these guys would be equal in terms of hold on. Okay. I'm having a hard time today. Nothing is working now. My laptop is frozen. So these two would be equal compared to their stability. In both cases, because you have oxygen in both cases, oxygen likes a negative charge compared to that carbon. So we're kind of good in both these situations. All right, so these guys would be predicted as equal stability. Okay, so in this case, because F has an incomplete octet, this carbon here is missing one of its electrons, then it's going to be less stable than E. E is going to be more stable. Okay. So in this case, G is going to be more stable than H. And we know this because for two reasons. What are the two reasons? That's right. The oxygen has a positive charge and the carbon has a negative charge, right? So we have a positive charge on the most electronegative and a negative charge on the most, that should be more electronegative, more electropositive atom. So. Okay, so in this case, J has greater stability than I because the negative charge is on the oxygen, making it more stable, right? Where if it's on the carbon, it's going to be less stable. Okay, so if we break it down, stability is going to be easily predicted if we have an atom that has an incomplete octet. They're going to typically be less stable. If you have a negative charge that isn't on the most electronegative atom. If you have a positive charge that isn't on the most electronegative atom. If you have a negative charge that is not on the most electronegative atom. So, and then if you have charge separation. Okay, so delocalization energy. So delocalization energy is basically the energy that's going to be associated with the extra stability of the compound. And then that's going to end up resulting in delocalized electrons. So we already know that delocalized electrons are also called resonance. You guys are already aware of that. Therefore, delocalization energy is going to be equal to the resonance energy. And resonant hybrids are going to be more stable than any of the resonant contributors that are predicted to be. So stable resonance hybrids are going to be the best rather than the ones that have the unstable versions, like the negative charge on the carbon or the positive charge on oxygen. So the greater the number of relatively stable resonant contributors, the greater the delocalization energy. So the more stable resonant structures that you have, the more delocalization energy is going to be associated with that. Okay, so for instance, so the delocalization energy for the carboxylic ion is going to be greater than that of the carboxylic acid. So this is the carboxylic ion. This is the carboxylic acid. So in this case, this guy has a higher delocalization energy because you have two resonance structures that are both stable. Where this one, you only have one stable resonance structure, relatively stable. So resonance structure, okay? So this guy has greater delocalization energy because it has more stable resonant structures, okay? Okay, so in this case, we have an unstable resonance structure, we have a stable resonance structure, and an unstable resonance structure. Where in this situation, we have three stable resonance structure. Which one is going to have the greater delocalization energy? Say it again. The one with three. That's correct. So we know that this one is going to be more stable. I mean, have greater delocalization energy than this guy would. Okay. So the greater number of relative stable resonance structures, the more nearly equivalent their structures, the greater the resonant energy is. So these guys are pretty much identical in terms of their resonance structures. So in that case, these guys have equivalent, so it's going to have a significant delocalization energy because there's two resonance structures relative compared to, in this case, where we only had one. Okay. Okay, so in summary, the greater the predicted stability of the resonant contributors or the resonant structures, the more it contributes to the resonant hybrid. The greater the number of relatively stable resonance structures, the greater the delocalization energy. The more nearly equivalent resonance structures, the greater the delocalization energy. Okay. So this here is considered a isolated diene. So it's considered to be isolated because you have you have your diene on one end and your diene on the other, right? And then you have single bonds that would be isolating the double bonds. Where this here is going to be considered a conjugated diene. So you have only a single bond separating between the two dienes. So if we take a look at our say 1,4-pentadiene compared to 1,3-pentadiene, and then we look at the change in enthalpy of the reaction. Oh, what type of reaction is this, by the way? That's adding hydrogen to it. With the use of palladium and carbon as a catalyst. Sorry, palladium, palladium, palladium. No, it's not. It's hydrogenation. Yeah, it's also written on the board, right? Hydrogenation. So we know that this is a hydrogenation reaction, right? We're adding a hydrogen to it, right? Generating hydrogenation. Okay. So in this case, we're going from double bonds to single bonds, but the energy that is going to be associated with it, if it's an isolated, its enthalpy is minus 60.2, compared to if it was conjugated, it's 50.1. So that means the conjugated form is going to be more stable than the isolated form. It also, in this case, its enthalpy reaction is going to be smaller. Its heat is going to be smaller. And that's going to be, the smaller the heat, the more stable the compound. And that kind of makes sense, right? Because you would assume if it's more unstable, the more unstable it is, the more release of energy you're going to get, right? So that means that the conjugated form is more stable than the isolated form. Does that make sense? Okay, so conjugated dienes are going to have delocalized electrons. So this here would be one resonance structure. That would be our starting. You guys cannot see what I'm circling. How about now? See it now? So this is going to be our starting structure. So this is our conjugated diene, right? Compared to our isolated diene, so our conjugated. So then this here would be one resonance structure. This would be our other resonance structure. Okay. So this here is how we would draw it as a delocalized electron. So this is showing our resonant hybrid. So knowing what you guys know, stable-wise, stable, less stable, more stable, less stable. Which is going to be the most stable of our resonant structures, our resonant contributors, or are they all going to be stable? Or should I say, are they all going to have the same relative stability? Be the correct way of phrasing it. You said the same? Are you sure? Based upon what you guys have just learned, so this resonant contributor compared to this resonant contributor. Okay. So if we're comparing these two, which one would be more stable? The one in the middle. Why? Okay, because there's no negative charge on the carbon or no positive charge on the carbon. Because here we have separation of charges, right? So that's going to be less stable than this guy, right? Okay. Okay. So your sp²-sp² bond is going to be stronger than your shorter sp²-sp³ bond. Okay. This guy has the sp²-sp². Okay. Where this guy is going to have your sp²-sp³. Okay. Okay, so stronger bonds are going to cause things to be more stable. And so if you have that sp²-sp², it's going to have shorter and stronger bonds. Okay, so this helps us understand that bond length. Okay, so this is an sp²-sp², sp3, sp3, right? So its bond length is going to be 1.54. So in the center carbon here, right here, so if we take a look at this, the bond here, is that going to be, sorry, the center carbon is going to be what type of bond? sp3? Okay, are you sure? sp2. 1, 2, 3 attachments, right? So then it has to have three things. It's going to have one S and then two P's. Yep. Okay, where this guy here is going to be this carbon here. This guy's going to be sp3. Yep. So in this case, you have an sp2, sp3. So in this case, then you're going to have a 154 bond length. So in this case, you have this carbon here and this carbon here. That's going to be what? sp2, sp2. Okay, so that's going to have even smaller. So if we looked at this, which one is going to be more stable? The sp²-sp², because it has a shorter bond. Okay, so then this guy has an sp3-sp1. It has a shorter bond length. So in terms of stability, more stable or less stable? More stable, because the shorter the bond length, the shorter and the stronger the bond, right? The more stable they are. Okay. Questions? Concerns? Okay. Okay. The allenes. So allenes are basically when you have two double bonds that are kind of right next to each other, or cumulative. Okay, so then in this case, your center atom here is going to be sp. These are going to be sp3, sp3. Okay, and this is considered, again, cumulative because you have double bonds that are right next to each other. So these molecules are basically going to be used for, come on now. Are going to be used for aspects of like trying to conduct electricity. So because you can get electrons moving along those carbon chains. So by donating those electrons, they'll be able to move. So a lot of times the way that we can do this is by doping those carbon chains. And so like this is basically used for like our LED screens. And so an LED is basically made upon this concept. And so here we're just getting electrons that are going to be able to move from bond to bond to allow that effect to happen. So organic compounds can be used to conduct electricity if we kind of set them up by doping them. Or priming them so that you're short an electron, so, or you get that separated charge. Come on. Okay, I want stuff to work. I need another computer. So I've decided. Okay, so we have Allyl and Benzyl, Allyl, Benzyl, and Allylic and Benzylic. So we've talked about this before. Allylic is just a double bond that has in this case, a cation positive charge associated with it, right? So, and then benzylic is just that benzene ring with a carbon attached that has a charge associated with a cation. So an allylic carbon is going to be that carbon, it's literally that carbon that's off from the double bond. So it's one away from the double bond. You guys, we actually talked about allylic and allyl and vinyl. You know, vinyl is also a case where you have the double bonds, and then it's not that one that's one off, but it's a couple of ways off. So this guy is going to basically have the benzene ring, and then you have your carbon here is going to be charged. It's going to be a cation, and then on the other side you have carbon chain. So if we go with the resonance structures, okay, so if we go with resonance structures of an allylic cation, it's just we're changing, we're donating these electrons so that we form a double bond here. So now we have a single bond here, double bond over here, and this guy becomes charged. In the case of the benzylic, the double bond here is going to be donating the electrons. So then this guy then becomes charged. And then we could get the donation of electrons from this guy. So then it'll be charged over here. Then we could get donation of the electrons from this double bond. And then this position becomes charged. So the sixth position becomes charged as a result of that. And then we could donate the electrons from here, and then we end up with exactly where we started. Only thing now we have double bonds that have been altered, right? So staggered the other way, right? So then these are 1, 2, 3, 4, 5 different resonance structures. So if we're comparing the two, 1, 2, which one is going to have the highest delocalization energy? The benzylic or the allylic? Okay, why? Because it has more resonance structures. Now, are you guys getting the point with OChem? A lot of memorization, not as much calculations, right? I know this is the part that you guys hate because you guys are very calculated oriented, like me. So obviously you can tell who your instructor was. I corrupted you guys. So, but we want to start trying to think of these, like, again, the pictures of it. Try to remember what they look like, and they kind of set up things, right? So here, this is going to put everything in terms of our carbocations, right? So this is the whole list of carbocation stability. The benzylic cation is more stable than the allylic. These guys are approximately equal. Sorry. Okay. Then we have the tertiary is going to be about the same as the allylic, or the Allyl. The secondary is going to be less stable. The primary is going to be less stable than the secondary. The methyl cation is going to be less stable than the primary cation. And then the final cation is going to be the least stable. So having that positive charge on the carbon that has a double bond attached to it, least stable. Okay. And you guys see that, right? Yeah, that look, simple. Okay, it's not coming up that good. Yeah. Okay. Okay, so here we have a tertiary allylic cation. That's going to be more stable than a secondary allylic cation. And then that's going to be more stable than just the allylic cation. And you guys see the distinction between them, right? Tertiary basically means that you have hydrocarbons here, and you have this third hydrocarbon attached to it, right? To that center carbon. Here, secondary means that you have two hydrocarbons attached, and just the allylic is just having that single hydrocarbon attached here, and where you have hydrogens on the other end. Okay. Tertiary benzylic cations are going to be more stable than secondary benzylic cations, which are going to be more stable than just the benzylic cation. Okay, so, and we know that these guys are comparable in stability, right? Roughly, give or take. Although we know that in terms of energy, this guy's going to give us more energy. So it's going to be maybe a little bit better. Or delocalization energy. Okay, so do you guys remember MO diagrams? Molecular orbital diagrams? Where you have two things that are coming together to, and you have sense anti-bonding and bonding. You guys had it like, yeah, you know, we saw it. Okay, so this is just that diagram. So this is that energy diagram. And this here represents the bonding. So this would be our pi bonding. This here would be our pi anti-bonding. Okay. And then so this would just be, sorry, this here represents that p orbital. So these are the two p orbitals that are coming together. These are the two p orbitals that wouldn't bond with each other. And usually you guys remember that has to do with the orientation of the electron, in a sense, that whether or not they're going to be bonding and anti-bonding, but that happens when we put them in the shells, like we bring them together. Yeah, no, maybe. You hated this part? Yeah. Well, yeah, this is why, yeah, it's not pretty. It's not. A lot of instructors in general chem just skip over it because, yeah, that's not nice though, because then you get it in this class and you're like, what the hell is that? You know, you need it. You need to understand it, right? At least minimal. Okay, so in the case of this situation, we have 4 pi electrons that are going to be delocalized over 4 carbons. Okay, and they're basically showing us here. You're getting a delocalization that's happening all over 4 carbons. In the case of the 1,3-butadiene. Okay, so here's a molecular diagram for that, maybe. Okay, so this here represents the energy for a P subshell. So here we have the 4, where we have 2 of them that are bonded together, but the other 2 that are also bonded together, but since they're oriented differently, you have that separation between the 2, so you don't get complete bonding. Where down here, so this would be anti-bonding, this guy would be bonding. This would be complete anti-bonding. This guy is where you have just those center P bonded, where these guys are anti-bonded. Okay, and so this here is going to be representing the molecular orbitals of the 1,3 butadiene. Okay. Okay. So this here means this shows us symmetric. So these guys would be symmetric to each other. This guy would be symmetric, where these guys would be asymmetric to each other. Make sense? Where symmetric basically means like mirror images of each other. Symmetry, cut it down the line and you get exactly the same thing, right? You cut it down the center, you get exactly the same thing. Where these guys, you cut it down the center, they're 2 opposites. Same thing here. Okay. Stop yawning. Mauricio, it's contagious. Okay, so then we have localized versus delocalized. Okay, so here these are going to represent our localized. So these are your pi electrons that are going to be localized. And then these are going to be your pi electrons that are going to be delocalized. So in the case of the 1,4 pentadiene, so we have pi electrons that are going to be delocalized, localized. Where in the case of the 1,3, we're going to have pi bonds that are going to be delocalized. Okay. So the delocalization of electrons are also going to affect how acidic things are. Okay, so we have ethanol versus acetic acid. Okay, so we know that acetic acid is going to be more acidic, acetic acid, hence, right? It also has, is it going to have more delocalization energy associated with it? Is it going to have more delocalized electrons or not? No? Are you sure? Or you're just saying, I'm just going to say an answer because I'm either going to be right or I'm going to be wrong. What was that? Okay, so I said, is acetic acid going to have more delocalized electrons than ethanol? Yes or no? How many of you guys say yes? How many of you guys say no? So what is the concept of delocalized electrons? When are they delocalized? When what? When they're moving from atom to atom. Okay, so if we do the electron configuration of each of these, just for kicks and giggles, right? So this guy is pretty much already set up. Only thing we have two more electrons here. Those are electrons. They're fat circles. Okay. Now we know that here we just have these electrons here. Okay. Are electrons going to be moving in this case? Are these electrons going to be delocalized? Are they going to go anywhere? No. But this guy is going to have another resonance structure associated with it, right? Okay. Because we could end up with the double bond being over here and this guy being a plus and that being a minus. Minus, plus, right? So we know that this guy has the ability of having other resonance structures. Because of that double bond, we could actually do this over here. We could do this over here, which is a lot less likely, but we get that going, right? And then we would get a resonance structure for it. Well, the more resonance structures that you have, the more acidic it's going to be relative to other things. This guy doesn't have as many resonance structures. It's going to be less acidic. So the more acidic that it typically is, yes. So in the case, carboxylic acid is going to be a stronger acid than ethanol because of the inductive electron withdrawal and electron delocalization. So because we can sit there and remove two things, right? We can remove this H plus, right? And so then if we do that, then that's going to end up resulting in electron withdrawal because this guy becomes O minus, right? And then we're also able to get delocalization. So it's 2 in this case. But we also know that acetic acid is an acid by name, but it's also going to have a lower pKa. It's going to be more acidic. Its acidity is going to be greater. So typically, if you have delocalized ions, you're going to have more acidity associated with it compared to something that may not have that. Okay, so which one's going to be the stronger acid? Ethanol, ethyl alcohol, or ethanol, or vinyl alcohol. Okay. Because I wanted you to write them down. I didn't want you guys just to give me the answer. Okay. So in this case, oh, you want me to go back? Because it has more delocalized electrons, where this one doesn't, right? This one does. So it's going to be more acidic. And again, it's going to be a relative type of thing. So relative to each other, this one's more acidic. Okay, so proton loss is going to be accompanied by an increase in delocalization energy. That makes sense for what we saw. So if you're able to lose a proton, then that's going to increase your delocalization energy. So in this case, here we have acetic acid, right? So this was the relative unstable version where we have a minus and a plus over here, right? And then in this case, this guy is going to be more stable because we've lost that proton, right? So in the case of the acetate versus acetic acid, this guy is going to have higher delocalization energy because we know we have those two resonance structures that are more stable. And the electrons, the negative charge is on the oxygen, which is the more electronegative atom. Or in the case here, you have a negative charge on the oxygen, but you have a positive charge on this oxygen. So in the case of the acetate, the negative charge is going to be shared by both of those oxygens, by two oxygens. Okay. So we know that in the case of phenol and cyclohexanol, phenol is going to be more acidic. Why? Because it's going to have more resonance structures. Okay. And actually, cyclohexanol doesn't have any delocalized electrons, where the phenol does. So therefore, phenol is going to be more acidic. Okay, so here's the phenol. So these are all of the resonance structures for phenol. Okay. And so if we take a look at the conjugate base is going to have a greater delocalization energy than the acid because it's gotten rid of that H plus, right? It's gotten rid of the proton. So that gives it a little bit more, okay? Even though this is more acidic than the base. Okay, so if we take a look at protonated aniline versus protonated cyclohexamide. So in this case, same thing. Lower the pKa, more acidity compared to the protonated cyclohexylamine. So, and that's because again, the protonated cyclohexylamine does not have delocalized electrons, where the protonated aniline does. And so aniline is actually going to be greater delocalization energy than the acid, although the acid was more acidic than not having any double bonds to transfer anything. Okay, questions? All right, so this is kind of important. Okay. Yes, because it's gotten rid of the H plus. If that's only if there are things that are delocalized, because here these guys don't have anything that's delocalized, right? And so that's also part of the reason. So if you have something that's delocalized and something that isn't delocalized, the one that's delocalized is going to be more acidic than the one that isn't delocalized, okay, or delocalized electrons. And then if we're comparing the base to the acid, the base is going to have more delocalization energy because that H plus, because now you have the ability to use those electrons for more movement. Okay. Okay, so, and this kind of helps us in terms of chapter 2, we're talking about the acidity. That does not work out right. So these are the approximate Ka values. This should be less than the less than sign here. That should be the less than sign here. That should be the less than sign here. So let me draw that in. Come on. It just screwed up. Did it show right on your guys' handout? It says squares. Okay. So, okay, so we have the hydronium ion here. So its pK is going to be less than 0, right? And that's typical. We know the hydronium ion is what makes an acid an acid. So if we just have hydronium ions, its pK is going to be less than 0. If we have a carboxylic acid, which this is the root for carboxylic acid, its pK is going to be less than 5. So like acetic acid, citric acid, oxalic acid, right? So those are all examples of carboxylic acids. Okay, this here is an amine. Sorry. So amines, these protonated amines are going to have charges that are going to be less than 10. And that's the same thing with the benzyl alcohol as well. And then in the case of the alcohol, they're going to have pKs that are going to be less than 5. I mean, less than 15. And that's the same thing with water. Okay. Questions, concerns, Cash? Okay. How you guys doing so far? Good. Okay. So another way of looking at it, so the electronic effect, right? And so in other words, if we take a look at this, here is going to be the electron donors. So the electrons are going to be moving from this item to this item. And this here is going to be, this guy's going to be actually withdrawing the electrons, right? Sorry, right? Yeah. And so electron donors are going to be destabilize the base by increasing the electron density on the oxygen. So the oxygen over here, its electron density is going to increase, basically meaning that the electron is going to be going over here. So you guys remember polarity, right? So this is what you're just looking at, is the polarity, right? So the electronic effect is the the look at polarity and how that electron is basically moving across. So in this case, the electron density is moving in this direction, right? Okay. In this case, this is when the electron is going back the other way. So in this case, so because it's being shared between them, the electrons are constantly moving, right? Even though it's spending more time on this side, the electrons will be spending more time on this side. It's still going to have to go back to the other side because it's being shared, right? And so this is that electron withdrawal. This is the electron donation. Here, the electron is being donated to this oxygen over here, to that cloud, to make it bigger. It's going to spend more time in that direction than it is going to be spending in this direction where it's being withdrawn. Okay, where it's withdrawing from that high density cloud and being pushed back over here. And then in this case, you're getting those resonance structures. This guy is moving this guy, which is moving this guy, which is then this guy. Okay, does that make sense? So have you ever, I'm trying to think. See, all I can think of is Knight Rider, where you guys never saw that show. There's this game in like little arcade, like Dave and Buster's and everything like that, where the goal is to try to get the ticket. I get the light that goes around in a circle and has to line up perfectly in this right spot and get it. And so, but there's a point where the light will do this. Doom, 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 doom. Have you guys ever played Pong? It's the game where the ball goes back and forth. What was that? The Atari game, yes. See, I'm dating myself, right? Okay, so the electron is kind of like that. So it's going to be going from that side that is the pole that is positive, partially positive, to the side that's partially negative. But it's going to be constantly moving. Now it's going to spend more time around the side that's partially negative than it's going to be spending on the positive, but it has to go back to that side. So your electrons are going to be, the effect of your electrons are going to have that same effect, particularly on carbon molecules, because you have this guy who's electronegative way out here. It's going to be affecting the other parts too, and so you're going to get the electrons kind of collapsing in that direction and spend a lot of time over here, and then that electron is going to have to go back. Okay, so electron donation decreases acidity, right? So if we're getting electrons being donated, the acidity is going to be increased. Okay, electron withdrawal, the acidity is electron withdrawal is going to increase acidity. Is that right? Yes. Decrease donation, increase. Okay. Okay. So if we have that electron effect going on, it's going to one side or the other. So a moment you're increasing the acidity, but for a while. Then the other moment you're decreasing. But there's going to be a balance depending on how frequent that electron is. So we take a look at that at one given point. You could have a point where your acidity, technically, if you're looking at a single molecule, one point where your acidity is less than the other. Right? And so often when we get that fluctuation in the pH meter, it's a result of your poles being played with a little bit. But eventually you get the stability that goes on. Does that make sense? Because electrons are always going to be moving and depending on the movement of your electrons. Now, the overall, in the case of having this negative charge here and the fact that this guy is going to be electronegative, the overall goal is going to be, or the overall, if you take it, all of the molecules at a given point, they're going to be spending more time over here around that cloud than on the other side. So then overall, it's going to be the electron donation, which means that your acidity is going to be up or down. Down. Okay. So you're going to have a decreased acidity as a result of that. Okay. Does that make sense? Okay, come on. Okay, so here, same concept, right? So instead we have nitrogen. So here we're going to have electrons that are going to be donated. Let's see, substitute withdraws electrons. Okay, so in this case, because of this plus, we're going to be inducing the electrons to be pulled this way. So then in the case of inductive electron withdrawals, so in other words, by having that charge, we're inducing the electrons to be pulled that way. We are, and what was that? So it's increased its acidity, that is correct, right? So in this case, we would expect, which kind of makes sense. It has a plus charge on it, right? So you would assume that it's going to increase it. So this inductive electron withdrawal is going to be basically withdrawing through sigma bonds in this case, because all of the bonds that are going to be associated with the hydrogen are going to be sigma bonds, right? Come on. Okay. So donation of electrons by resonance. So we're donating electrons. What's going to happen in this case? We're going to have a decrease in acidity. And this here just shows you those electrons being donated. Here. We got separation of charge. This guy's now negative. The guy's negative here. This guy's negative here. This guy's negative here. And as a result of it, we're going to get a decrease. And then what about in the case of withdrawal? Okay, we're going to get an increase. Okay, so this is just basically showing you withdrawal of electrons by structure. So now we have that plus that's here. So then this guy becomes negative, it's plus, plus coming over here, plus coming over here, plus coming over here, but back to here, and then it cancels itself out. Okay. So this is just going to show you the electron effect. So these are phenols, right? So when we have the so this here is a general phenol ring, right? So then when you have a hydrocarbon, oxygen, hydrocarbon, you guys remember the structure of that? What is it called? Where you have oxygen between the two. Was that? Okay, so we have an ether. That's correct. Okay, so in this case, this is a form of an ether, right? So, but it's a phenol methyl, so phenol methyl ether. Methyl phenol ether. Okay, so in this case, this guy has the acidity of 0.20 compared to in the case of the phenol. Phenol had the lower one, right? And we know because in this case, are we getting, based upon what we saw prior, because we just showed this, are we getting withdrawal or donation? Donation, because of the oxygen is going to be donating the electrons in this case, right? So then its pKa is going to go up or down, or its acidity is going to go up or down. acidity goes down. That's right. So then this value gets bigger, right? Because the lower the value, the higher the acidity of the pKa. Okay. And so that's the same thing that's going to happen here. Here we have delocalized electrons in here, but on the outside, they're not going to have much of an effect. So here, we're going to be having electron withdrawal, right? Because the electrons are going to be being pulled here away from the oxygen over here, right? So then in that case, what's going to happen? It increases, and that's exactly what we see. And that's the same thing when we put an oxygen double bonded over here, and then when we put nitrite on the other end of that, then it also will increase the acidity. Okay, and so we can kind of see the effect throughout the entire thing by what's attached to the other end of the benzyl ring. Okay. Questions? Concerns? Here? Yeah. This one, because oxygen is also more electronegative, right? And so you're, in a sense, you're going to be pulling it here. The electrons are then these electrons are going to surround this guy, right? And then, so it's going to have another pull effect, right? And because you have that double bond here, it seems to have more effect than the chlorine or a bromine. But if you had something like a fluorine or something like that, that would be different, because then it has a much stronger electronegativity, much more electronegative. And then this guy, of course, is going to have a much stronger effect, because here you don't have a carbon, right, that's affecting it, right? Instead, you have the nitrogen, which is also going to have a strong electronegative pull itself, right? In addition to the oxygens attached to it. So, does that make sense? So if we think about the electronegativity, even though you had a carbon here, the carbon just kind of shifts that electric pull, that electronegative pull. Of course, this guy won't be as electronegative as if I had, let's just say, the O minus, right? So if I just had O minus attached here entirely, then that would have more electronegative pull. Or say O plus would be unstable. But yeah. Okay, questions, concerns, Cash? I can't get it to work. Okay. So the electron delocalization can also affect products of the reaction. So we know that when we have this reaction, in theory, we have the possibility of having two products. We can have bromine being put here, or we could have bromine being put here, attached on that carbon, right? So those are your two options. So those, in theory, should be your two products. But because delocalization of electrons affect your products, you're going to favor being put on the carbon that is closest to the benzene ring, the benzylic ring, okay? Because of the, say, I guess in this case, withdrawal, that would be here. And so you're going to be favoring this product over this one. This guy's going to happen at a slower rate than this guy. So this guy is going to be the favorite product. So a secondary benzylic carbocation is going to be more stable than a secondary allylic cation. So this guy is going to have more stability. Since it has more stability, then you're going to get more of this product. Right? This guy's going to be less stable. So in other words, because you're having both of these, let me show. You have both these resonance structures existing. However, this guy is less stable. So then it's going to be pushing more towards this direction, right? So then it's going to be pushing more towards this direction. So then you're going to, as a result, get more of this product rather than this product. Does that make sense? Because this guy lacks stability. As soon as he gets a chance, it's going to get to this point, right? Because it's going to be, resonant structure is that movement of electrons. This guy's not stable. It's not going to sit here long. It's going to move almost like that to this resonant structure. Okay. How you doing? I know it's getting dry, right? Okay, so if we looked at, now let's talk about structures of isolated and conjugated dienes. So in the case of isolated and conjugated dienes, you guys remember the structure isolated, where you have single bonds in between the two between the carbons between the two dienes, and then in this case you just have a one single bond between the two. So this guy is isolated, this guy is conjugated. So in the case of reactions with our isolated dienes, if you have excess hydrogen bromide, then we're going to end up with bromine being attached to our second, and in this case, our fourth carbon. So 2 and 4 carbons. 2, 4, 5, sorry. 2 and the 5th carbon. That was in the last bond. So then it's not going to be attached to the terminal carbon here, nor is it going to be attached to this terminal carbon. It's going to be attached to those internal carbons. Okay. Now, the way that that's going to happen is that this double bond is going to donate its electrons to our bromine, to the hydrogen on the bromine, and then the bromine, the hydrogen is going to donate it to the bromine, right? So then you're going to end up with your bromine, or the hydrogen is going to then attach to this carbon, so then making our carbon H3. And then the bromine is going to be able to, now because this bromine is minus, this carbon is going to be a plus, it's going to then attach to here. And since you have excess, that's going to be the same thing that's going to happen over here. And if we had another chain, if the chain continued, it would happen the same way over here, right? It went further, okay? So, and this is just basically showing you that. Okay, so the electrons are being donated to the hydrogen. The hydrogen then donates the electrons to the bromine. Bromine becomes a negative charge. This guy's a plus charge. This guy gets together because that plus and minus and forms a bond. And then we get the formation of this guy, and then the same thing happens over here. Exactly the same process. So there one bromine for, if you have excess, yes. Yeah, and then the key is that's right. It has the ability to do that, because then what would happen is that you get the first breakage, and then you get that, and then you have the potential of getting others along with that. So depending if there's excess or not. So it just depends. And that's the key. It's like, that's right. That's right. Yep. Okay, so if I have 1 mole, 1 mole to 1 mole, so equivalent, right? So in this case, we're not going to even touch this guy at all, right? This guy is going to be our prime because it has more stability than the terminal double bond, okay? So we're going to get a hydrogen attached here, chlorine's here. So in this case, it's going to be, again, the electrons are going to come from here onto the hydrogen, then the bond between the hydrogen, that's going to make this guy Cl minus. It's dots. This guy's going to become a plus. Cl minus is going to attach right here. Okay. Questions? You doing okay, Mauricio? Okay, so do you mind if we take a 5-minute break? Okay, so if we go with conjugated dienes, so if we have equal parts, in the case of chlorine gas, so then it's going to go with one end or the other. It doesn't matter which one. So it's going to either be, I guess either one, it'll be the same product. So you're going to end up with either 1, 2, the 1, 2 position, or you're going to end up with the 3, 4, which is, if you flip it around, it's still 1, 2. So in that case, okay. So, or you can end up with 1, 4. And in the case of the one conjugated dienes with equal parts hydrogen bromide, then you're going to end up with a 1, 2 addition. So you're getting a hydrogen on the 1 carbon, and then on the 2nd carbon, you're going to get the bromine. So the bromine is always going to go in the inner carbon. Or you could end up with a 1, 4. Okay. And then in the case of the 1, 4, it's no longer that inner carbon. Now you also get movement of your, because your resonance structure, you're going to end up with that double bond being here. And then that makes this guy more accessible, the ends accessible. So, okay. Are you with me? So, and again, in both of these cases, that's a result of your different resonance structures. Check it out. Okay. So if we have 2, 4 hexadiene, so is this a conjugated or is this a isolated? First off. This one right here. Conjugated or isolated? Was that? Conjugated, yes. It's conjugated, right? Because it only has a single bond between it rather than having, okay, 2 single bonds. Okay, so if we add equal parts of bromine, then we're going to end up with either 1, 2 bromo hexodiene, or we're going to end up with 1,4 hexodiene. Both of those products are going to be available, again, because of the resonance structures. Okay. So the mechanism in this case, double bond, is going to provide the electrons for this guy. And then you're going to get your 2 bromide ions, and they're going to attach there. Okay. So this is just showing you the mechanism if we had hydrogen bromide. So again, double bond is going to provide the electrons. Electrons are then going to be shifted over to the bromide. You're going to get bromide minus, bromide, and an H plus. So then your H plus is going to go here. Your bromide is going to go on that second carbon. Okay. So alternatively, you'll have this possibility where you have your bromide, your H plus, sorry, your H goes here, but then you shift the positive charge by delocalization to the end carbon. So then your bromide would then go to that end. Okay, so in other words, you end up using these electrons. The electrons go here. This guy becomes neutral. Then this guy is going to become plus as a result. So then your plus is now able to be accepted here. And so then you end up with your 1,4 product. You guys see that? Okay, so your 2 possibilities, right? Then there's more possibilities. Yeah. Yeah. The more resonance structures that you typically have, the more possibilities that you could have. But it also depends on the stability of your resonance structures. Since these resonance structures are going to be comparable, right, to each other, right? So then, since they're going to be comparable to each other, then you have the possibility of both, right? If you have one that's a lot more stable than the other, Majondit, yeah, most abundant, Majondit. The most abundant form, yes. Okay. Okay, so does C1 or C4 get the proton? Okay, so then protonated end of the end that forms the more stable carbocation. So that is going to be our determinant on whether the C4 or the C1 gets it. Let me clear that off so you can actually see. Okay. So if we look at this, these are your resonance structures. Okay, so in this case, so carbonation formed by adding the H plus to the C1. So if we add, so if we're adding it to this carbon here, then this guy is going to end up being plus. Then we're going to get formation of this resonance structure. Okay, so, and then if I add it to the 4th carbon, then in this case, add it to the fourth carbon here, then in this case, then double bond is going to go here. And so we're going to end up with the plus at this end. So in terms of our resonance structure. So here's 1 and 4. So in the case of this guy's going to give us our 1, 2. So we'll end up, since we have 2, we have the plus on this product. So then the bromine is going to be added here, or the bromine is going to be added here. Okay. Questions? Okay, so kinetic versus thermodynamic products. Okay. So what does kinetic mean? It means motion. Yes. So we talk about kinetics, we're talking about motion, right? Thermodynamic would mean temperature, heat. Yep. Okay, so thermodynamics is basically changing temperature, changing heat. Okay, so in other words, we could have products that are going to be favored based upon motion, or where the electron is moving to, right? Or we're going to have products that are going to be favored based upon temperature, right? So both of these products are going to exist. This guy favors the kinetic component. This guy favors the thermodynamic component. So what does that mean? Well, at really low temperatures, right? That means that we're not putting energy into the system, right? We're basically just letting the kinetics go. So then most of your products are going to be in this form, okay? Where it's on the 1, 2, okay? So you're going to have a 1, 2 addition, okay? In that case. Now, if we up the temperature, so this is at minus 80 degrees. So if we up the temperature, then, oh, and I should also add, this is it becomes an irreversible reaction. You're only going to get those products. If we up the temperature, we get a reversible reaction, but we're favoring our product side, and we're favoring the thermokinetic, or the thermodynamic part, thermokinetic, the thermodynamic component. Okay. So depending on the temperature, we could sit there and favor one thing or one product or the other. Okay. So why? Why does that work out? Come on. Okay, so this is the free energy, Gibbs free energy diagram. Yes. Okay, so do you remember that delta G? Okay, that's called Gibbs free energy. So it's a combination of the enthalpy and so you remember enthalpy meaning heat, right? And the entropy. Entropy is order or organization, right? So Gibbs free energy is a combination of both of those, right? So depending on how well it's organized, so the more entropy you have, the more entropy, more entropy you have, the more disorder you have, right? That means that you're going to be pushing it to get order, right? So then that means your energy value is going to be high, it's going to be pushing it one way or the other. Enthalpy, enthalpy is, like I said, it's just heat, delta H, right? So it's just that the heat that is the formation of the reaction. So either you're putting energy into the reaction or you're taking energy out of the reaction. That's enthalpy. Together, they form the Gibbs free energy. So when we look at a chemical reaction, it's going to be dictated by order and heat. Okay, essentially, that's what it boils down to. Okay, so depending on how much order you have, you may need a certain amount of heat to get that reaction to happen. And depending on how much, or vice versa, the least order you have, you may need a little less heat, right? Okay. So in this case, in this situation, right? So this is our products. So this here would be, we first need to get over the hump, right? And then, so that's initially how we get to the reaction. So in this case, we're using the kinetics, the aspects, the kinetic part of the aspects to get over the hump. So as soon as we get over that hump, it was a minus 80 degrees Celsius, we're able to get our kinetic product, right? Just by the addition of it. So that means that the enthalpy, the heat that's involved is very minimal because it's a little bit, hardly no temperature added. We're at minus 80 degrees Celsius, right? So we really didn't have to put too much heat in to get the product to happen. It's happening on its own, right? So then you get the formation of this product first. So this product is going to happen before this product can happen. So then what happens in this situation is that if we added heat, right, or time, we get the formation of this, right? But this guy is our first product. We make more of that abundant product first. Now, when we add heat to this, we change that. We have a preference for this guy, right? Because now we're not only driving the formation of this guy is being pushed in that direction as well too. So you're getting more and more of this product. This guy forms a lot slower, right? But it increases as we increase the temperature, right? The formation of it. Okay. So that basically means that temperature can favor one product or the other, right? So depending on the temperature that you have, you can favor one product or the other. Okay. So questions? Okay. So in other words, they both have a common intermediate. Adding heat to our system favors this product. Keeping our system cool favors this product. So, kinetic control. So kinetic control, in the case of kinetic control, both reactions are going to be considered to be irreversible, meaning that they're only going to go in one direction. So one product is favored because it happens faster, right? And again, remember when we talked about relative stability, right? The one that typically is the most stable is going to be the one that's going to be favored, right? Of the two forms. So it's going to have the favoring of that one. So you're going to end up with, in this case, more product B than product C, right? So that's how we ended up with that 80-20 split. I think it was 80-20, I can't remember exactly. Okay. Now, in kinetics, right? So in thermodynamics, either one or both are going to be irreversible. Going to be reversible. Meaning that they can go both ways. So if that's the case, then if we're getting product B, well, guess what? We can get more product A coming back because we're getting a lot of this, and then it's going to drive the formation of product C. Now, if product C is irreversible, then you're going to get accumulation of this. This guy's going to be taking out more of product A. So then you're going to be driving this reaction this way. So do you guys remember Le Chatelier's principle? Okay, so Le Chatelier's principle basically said, let me do it in terms of a basic reaction first, and then we'll do it in terms of a this reaction. So Le Chatelier's principle basically says that if I have, let's say, NO yields N2 plus O2. Okay, so, and this is a equilibrium reaction or an irreversible reaction. So if I start taking out oxygen, I start removing oxygen out of the tank. So you can separate gases based upon their density or something along those lines. So I separate it and I get oxygen because oxygen's density is lower than nitrogen. So nitrogen sits up here, oxygen sits up here, right? Even though that they're, moving around and stuff like that, most of it's going to be down here. So I may be able to separate it, but I'm able to get that oxygen out. And I just twist the vial and then oxygen comes out, just oxygen. The nitrogen stays in there. So then that's going to cause this reaction to go in which direction? If I'm removing, because equilibrium basically means that the rates are going the same direction, but it's favoring one side or the other. Okay, so in other words, I'm producing this guy, right? If I'm removing my product, then I'm removing more of my product. Which way am I going to drive my reaction? Am I going to drive it towards the reactant? If I'm removing my product. So the product is being removed from the system, so I have less and less product. Now remember, it has to get to a point of equilibrium where you have comparable amounts. What was that? Not the same amounts. You got to be careful of that. The rates of them are the same, that are going in both directions, right? But what happens is that I'm changing my equilibrium. At this point, I have no product. If I remove my product, what am I going to do? Which way is the reaction? Let's say I only have reactants. Which way am I going to drive the reactions? I'm going to be pushing towards the product, right? So if I remove one of my products, I'm still going to be pushing towards the products because I don't have any oxygen, right? So that means I don't have any oxygen to push it back the other way. So I need to start making more oxygen so I can push it back the other way. So the reaction moves towards the product, okay? So it's shifting towards the product. Okay, so that's what's happening in this circumstance here, right? Because we have products that are going, we have this reactant that is going towards this product, right? But at the same time, we're removing our reactant. So if we're removing our reactant by the formation of this, because this guy is not able to go back. So we're constantly removing our reactant. These guys, to try to stay in equilibrium, this guy is going to constantly start going to this, which means that it goes to this, right? So then we get 80, or was it? I can't remember what it was, 60, 40, 60% this and 40% that, right? Because we're constantly moving this guy out. Does that make sense? Yes, no, maybe a little bit. So it's basically using Le Chatelier's principle, right? And so because of that, it's pulling it out. We're having to form more A, right? As A is being pulled out by the production of this, we're forming more A, which drives the formation of this. Okay. Okay, how you guys doing? Not bad. We're going to stop a little early today. I'm going to go to 2 more slides and then we'll stop there. If I can get my slides to keep going. Okay, so in the reaction below, why is it that the 1,4 product, 1,4 addition product the thermal product. Okay, so basically the more stable alkene has the greatest number of alkali groups bonded to the sp. So this guy is going to be our kinetic product. This guy is going to be our thermal product. And the reason why okay, that did not answer anything, did it? I have to get the right slide for this. So I will get back to you on this. But as we saw earlier, our thermal product is going to be favored in this circumstance, right? And I'll get back to you on a better slide for this. This is where we'll stop.